for life to be maintained. Okay. So let's have a break. Then we'll talk about protein synthesis.
Mention why it's
Okay, so now we have the blueprint. How do we make the car? Okay, and the way it does that is really also a very lovely scenario. It turns out that sequences of 3 bases in a row, they code for a certain amino acid. So you have GCA that codes for glycine or something like that. Okay? So every 3-letter code codes for means one amino acid. And so in DNA, 3 letters, 1 amino acid. The next 3 letters, a second amino acid. Eventually, this will translate into a dipeptide. The next 3, tripeptide. And so you do this for a few thousand, you get a protein. Okay? So that's how that information is used. But how does it actually read it? Okay? So what is used here is this is where RNA comes in as a workhorse. 2 types of RNA in particular, the so-called messenger RNA, which is the one that makes the Xerox copy of that particular page that you want to make this particular protein, and then a so-called transfer RNA that actually schleps with it the amino acids required to line them all up so that you get the polypeptide of the specific sequence. And so here is a simplified picture. You have DNA here, okay, and so there's a strand of A, G, C, da-da-da. Messenger RNA comes in, and this is the page 149 of your car manual. It wants to copy, and so it lines up and assembles UCG, the mirror image of that sequence. Okay? And that sequence is copied because that sequence, page 149, fix your light. In here, it's a sequence that makes a certain polypeptide. Let's say 1 hemoglobin strand or something like that. Okay? So once it's done that, it comes off. And then it is visited by transfer RNAs that have attached to them or associated with them the individual amino acids. So here's where the 3-letter code comes in. They are RNAs where they have CCU, which corresponds to a glycine, or CCU is attached to glycine, CGU is attached to alanine, and so on, UG and so forth. So they come along and they read the messenger RNA, and that's the sequence that we just copied. So this, if you wish, is the mirror image of page 149 of DNA. Comes off and is now tackled by what amounts to be back to the image of DNA. These guys are all now back to, these are the original bases that were part of DNA. Okay? So you do a double imaging, okay? So you get back to the original sequence. And then there's an enzyme that couples all these amino acids. So this strand here, which is the copy of the piece of DNA, lines up all of these guys, and they line up so that you can make the polypeptide with a appropriate enzyme. That's sort of in global terms exactly what happens. And we have a 3-base code. Remember that we have, therefore, the number of combinations of associating a 3-base code with the 4 amino acids, with the 4 bases, is 4 to the 3. That happens to be 64. So you actually have 64, way more than required for 20 amino acids. Okay? Such that actually some of these codes are duplicates, or the 2 different codes can code for the same amino acid. And in evolutionary terms, this is there for a variety of reasons, one of which, the most obvious one, is when one amino acid is particularly important for polypeptide function, you make sure that this is represented, but there are many other reasons why this is, stuff that you will get exposed to when you take biochemistry. And so since then, of course, these rudimentary type chemical understandings, now rudimentary, breakthrough chemistry in the mid-20th century, we've come a long way. Okay? And perhaps I remember teaching this in 2007, only 7 years ago, when the human genome was deciphered. That was a program that lasted, I think it was started in 2004 or 2003. It was thought to take at least 10 years, maybe a lot more. But the advances in automation, in analysis of these base sequences, including laser chemistry and the like, made this faster and faster and faster, so that eventually in 2007 they had the first blueprint, and now they have all the 3.2 billion base pairs in a sequence. And this has now become so fast that you can go on the internet and find a company that will analyze your genome. All you do is take an envelope, spit into it, close it, and send it off. And for $300 or $400, they'll give you your genome. So this has revolutionized this entire business, such that at the moment we are exploring furiously genetic engineering. So people who are critical say we are tinkering with life. Yeah, we are tinkering with life. We've always tinkered with life. Any medication that you give anybody tinkers with life or death, okay, with disease and so forth. So to me, it doesn't seem to be such a huge step. Although philosophically and ethically, there are issues when you go to the very essence of our existence. Chemically, there's no issue, but there are other aspects that come into it. Genetic engineering, so we have gene modifications. People are already tinkering successfully with replacing certain bases, changing the base sequence, so you're making artificial nucleic acids and artificial DNA. But even more profound is the finding that you can use other bases, unnatural bases, so to speak, and they function in these scenarios. So you're truly tinkering with the manual for your car, okay, so that alternative models of our own makeup are conceivable. Gene removals, new organisms, there it is, crops, foods. Of course, the enormous amount of advances are to be expected in medicine, and all of this will come forth in the future. Here's a little cartoon. The human genome's been unraveled. Damn it, I have to change the password. So the future is with you. Okay. I'm done. I'm just writing my 350th research paper, and I will still have a few years left to write some more, but the base of my existence has really been done, and you're going to carry forward what has been done by the previous generation. My generation screwed up this planet, and we've been busy trying to clean it up, but you will be going forward and clean it up some more, and also screw it up some more. Okay? So you will face the same kinds of problems as everybody else. And now on I think truly exciting scale, particularly when it comes to bio advances, but also in the materials advances. Okay? They are both equally exciting as far as I'm concerned, and this will truly revolutionize what we will expect very soon. So I hope I gave you a little bit of a glimpse of organic chemistry in the second semester, particularly how things work, that we're all surrounded by materials that are based on organic chemicals, that life itself, of course, is organic chemistry galore. I hope you took heed of my implorations of you to be critical. Okay? There's a lot of stuff out there. Newspapers report things in a way that sell the paper. You need to read between the lines. If you see an article about some breakthrough in medicine and they say something that doesn't sound quite right, look it up. You can go to the original literature or at least secondary, proper scientific literature reviews and the like, and you find out what to do. I hope that you're critical of your doctor. If you don't understand what's going on, if you have some ailment, look it up, check it out, see what's out there. Doctors aren't always right, and in particular, they're so busy dealing with insurance companies, they're not up with the literature. Okay? So I do this routinely, and I'm not nasty about it, but I always schlep around a review about whatever ails me, and I say, well, these guys say this and that. And typically, doctors say, no, this is interesting, can I have a copy? Okay? So there's established medicine and there's forefront. Not that necessarily forefront is always better, but it's good to be informed. Same thing with all the other stuff that's being pushed on you to be for consumption and the like. So I wish you the best of luck in your future careers, and also wish you good luck for the final exam. It's been a true privilege teaching you. Thank you.